Hello, eighth graders. Today we're going on to the next section in science, which is levers. We're going to really start digging into our next simple machine. Yesterday we talked about inclined planes and how that helps assist lift things or travel things over a distance. And so how having an inclined plane allows you to lift things that are heavier, but there's a trade-off that in order to have less force from yourself onto the object, you do have to go a longer distance. But an inclined plane helps you to do so without having to use the brunt of all of your force. Today we're going to talk about something called a lever, which is similar to an inclined plane where you're using something at an incline in order to leverage a different distribution of weight so that you can pick up heavier things. So we are on page 251. Levers 4.3.2. Have you ever used a screwdriver to pry the lid from a can, or played on a seesaw, or used a wheelbarrow? If so, you have used a lever. And we're just going to go over and look at the objectives for this chapter. So we're going to classify and compare different types of levers, calculate the mechanical advantage of a lever. So there's a formula in this as well. And then vocabulary, a couple things we're going to be talking about are the fulcrum, the point at which a lever pivots, and a lever, a simple machine made of rigid bar that pivots at a fixed point. A lever is a simple machine made of a rigid bar that pivots at a fixed point. A lever consists of two parts, a stiff bar that rotates and a fulcrum, which is the point at which the lever pivots. When force is applied on a part of the bar, the lever pivots at the fulcrum and overcomes a resistance force. Levers help move heavy objects. The Greek science Archimedes claimed that if he had a lever long enough and a place to stand, he could move the whole world. Levers are sorted into three classes according to the relative positions of the fulcrum: the effort force, or the force a person applies somewhere along the arm to make the lever pivot, and the resistance force, or the load to be moved. In a first-class lever, the fulcrum is somewhere in the middle. The effort force is applied on one side and the resistance force on the other. So if we were to think of that visually, if you had a fulcrum, which is our pivot point, we'll draw a triangle for that. Your pivot point is in the middle of your bar, okay? And this would be a first class. There we go. First class lever. So you have a long rod, and then in the middle, your fulcrum, your pivot point for a first class. So examples of these, the obvious one would be a seesaw. So seesaws, crowbars, and the claw of a hammer used to remove nails are classified as first-class levers. By shifting slightly forward or backwards, children on each side of a seesaw can raise or lower the opposite end, even if one child is smaller than the other. Similarly, to remove a nail from a piece of wood with a crowbar, a person pushes down on one end of the crowbar and the nail moves in the other direction. And so you have a picture down there on the bottom where you have, if your weight is on this side, okay, let's say this is your weight, this is your resistance or your output force. So output force. And the other side of your lever where you are putting the effort down is your input force or your effort. Okay. And then in the middle, you have your pivot or your fulcrum. All right. In a second class lever, the resistance force lies between the fulcrum and the effort force. Doors, Bottle openers and wheelbarrows are examples of the second-class levers. On a wheelbarrow, the wheel acts as the fulcrum, the resistance force in the middle, and the weight of the weight of the load. The effort force is applied to lift the wheelbarrow. It's exerted over the distance that the handles are lifted. For example, when a wheelbarrow is used to move a bag of dirt, a smaller force is exerted than would be if the bag were moved directly, but the force is exerted over a longer distance. Okay, so for a second class, you have, let's say this is your rod. Your fulcrum is at one end, your load is in the middle, and then your effort force is being lifted up. So instead of pushing down, like we saw, your input force or your effort was pushing down in your first class to lift. This time, our input or our effort force is being lifted up in order to move something over a distance. So this now is our input force, which is the effort. Our resistance is in the middle, so our output force. And our pivot or fulcrum is at the end. Okay. So you can see the difference in how it looks between picture and picture. So this one you're pushing down in order to lift something up on the other side. On this one, your weight is in the middle, your pivot point is down here, and you're lifting up in order to push something along. A third-class lever is very similar to a second-class lever, but there is one difference. The effort force and the resistance force change position. In a third-class lever, the effort force is between the fulcrum and the resistance force. A third-class lever does not change the direction of the force. The resistance and the effort go in the same direction. With this type of lever, there's always a gain in speed and distance with a loss in force. Examples of third-class levers include hockey sticks, tweezers, baseball bats, and tennis rackets. So if we're to draw out a third class, so a third class lever, you have your fulcrum, you're changing your space, and your resistance is down here. So we have the output force, and that's our resistance. You have your fulcrum here, or your pivot point, and then your input force is going this way. And that's your effort. Okay. So, like I said, a hockey stick, it's like you are the pivot with a hockey stick. Your output force is at the end of the stick. And so you're pivoting and you're pushing forward. You're going in the same direction that your output force is going to be going in. And it's in order to create speed. And so with that, or with tweezers, if you are pinching something, your pivot point is at the end and you're pulling out in the same direction that you want whatever it is you are pulling to come out. Some other examples they gave were baseball bats and tennis rackets. So again, you being the pivot point of the baseball bat or the tennis racket, and the input force of moving forward is going to move in the same direction as the output force, sending something forward with speed and force. You have learned that the mechanical advantage, or MA, of a machine can be calculated by dividing the resistance force by the effort force. For example, if the resistance force is 400 newtons and the effort force is 200 newtons, then the MA, the mechanical advantage, equals resistance force divided by effort force, which would equal 2. 400 divided by 200 is 2. But there is another way to calculate the mechanical advantage for levers. Because the distance from the force to the fulcrum also depends on the size of those forces. If the things are balanced, the mechanical advantage can be calculated by dividing the length of the effort arm, or the distance, the effort force from the effort force to the fulcrum, by the length of the resistance arm, the distance from the resistance force to the fulcrum. If the length of the effort arm is 2 meters and the length of the resistance arm is 1 meter, then your mechanical advantage is 2 meters divided by 1 meter, which equals 2. The mechanical advantage for our first and second class levers indicates how many times the input force is magnified when using a machine. When calculating mechanical advantage for a third class lever, however, the advantage will be a fraction. Why? Because it does not multiply the force. It actually requires more force than it puts out. The advantage is an increased speed. Inverting the fraction of a mechanical advantage determines how many times faster the resistance moves in that effort. Okay, and you have a couple pictures around there. You have pushing a dolly with a box is an example of a second class lever. So second class meaning the wheels would be the fulcrum. That's your pivot point. Your weight is in the middle, and you are lifting up your input force to push it forward. A hockey player with a hockey stick is an example of a third class lever. So the hockey player being the fulcrum, he is the pivot point. Your input force, the resistance, is your stick that you're using, and then your effort to push it forward. And then you have a hammer and a nail, which would be first class lever, as we read on the first place, as you have your pivot point in the middle. The middle of that head of the hammer rests on the wood. You are pulling in one direction in order to lift up the nail on the other side. So let's look at the try this. Place a wooden pencil on the table. Balance a metric ruler on the pencil. Place a quarter on each end of the pencil. If necessary, move them slightly to keep the ruler balanced. Stack another quarter at one end. This is now the resistance arm of the lever. The other end that has 1 quarter is the effort arm. Move the stack of 2 quarters until 1 quarter can lift the 2 quarters. Measure the resistance arm and the effort arm. Calculate the mechanical advantage. Add a 3rd quarter and then a 4th quarter, repeating the procedure each time. Which instance had the greatest mechanical advantage? What class lever is this? How do you increase the mechanical advantage? So what they're saying is, as you are balancing the two, to balance a ruler on a pencil, so you're moving the position of that pencil. So if you had, here's your pencil, if we looked at it this way, if this is your eraser, you have your ruler going across it, and if you have 1 quarter on this side and 1 quarter on this side, it's going to be balanced. If you were to add another quarter to this side, then this side is going to go down. Okay, that's going to be our resistance force. So where can you move your pencil, either this way or this way, in order for them to be balanced again? Where would you have to move that fulcrum? Okay, and then do it again, move it even in the middle. And then if you added a quarter to this side, where would you have to move that fulcrum in order for it to be even? And as you move that pivot point, as you move that fulcrum, you are actually making different classes of levers, either first class, a second class, or a third class, regarding where your fulcrum is, where your pivot point is. Okay, let's do some questions together. So number 1 in the lesson review, what is a lever? How would you define a lever? So if you go back to the first page, it has the definition of a lever there for you. Number 2, give an example of a first class and a second class lever. So they gave you some examples in the book. See if you can figure out or think of other levers that we use that would be examples of a first class and a second class lever. Number 3, what makes a third class lever different from the first and second class levers? So think about what is the purpose of a third class lever that is different than the first or second first or second class levers. Are you picking up something? Are you moving something by holding on to it and shifting it? Or are you hitting something in the same direction? So think about that as you're answering that question. Number 4, what is the mechanical advantage of a lever that uses an effort force of 90 newtons to lift a load or a resistance force of 30 newtons? What does this mean? So if we look at this, if we remember what our mechanical advantage formula is, so if we have mechanical advantage is equal to the effort. So if we have an effort force of 90 and a resistance force of 30, we're actually dividing those two things. So your effort force divided by your resistance force. And so if we were to divide those, our effort force is 90 newtons and our resistance force is 30 newtons. Oh, you know what? I'm actually doing that backwards. Should be resistance force by effort force. So if we have our resistance force, which is 30 newtons, divided by 90 newtons, we can reduce that fraction to 1/3. So our resistance force, the mechanical advantage is 1/3, and if it is a first or second class lever, it means that there's really no advantage. If it's a third class lever, the speed of the effort is increased by a factor of 3. That's kind of what we're learning here. So let's read that question again. What is the mechanical advantage of a lever that uses an effort force of 90 newtons to lift a load or a resistance force of 30 newtons, and what does it mean? So you have a 1/3 mechanical advantage. And so if it's a first or a second class where your lever is in the middle and you're pushing on one end in order to lift the other end, then you really don't have an advantage here. It's not going to help you too much. But if it's a third class lever, if you are saying hitting a hockey stick or a baseball bat to hit a ball, then the speed of your effort is increased by a factor of 3. Okay, so your mechanical advantage, your speed is increased. All right, number 5. If the effort arm on a second class lever is 2 meters long and the resistance arm is 50 centimeters, what is the mechanical advantage of the lever? Now, this is the formula they said for figuring out mechanical advantage based on the length of your rod, how long it is between the fulcrum and your endpoints. And so we have 2 meters here. So if you have, let's say this is our lever, okay? So, and we are on a second class lever. So on our second class lever, we're actually gonna put it down here. All right, here's our second class lever. And on our second class lever, we have the lever is 2 meters long. Okay, so we have a 2 meter long, and the resistance arm is 50 centimeters. So if this is here, our resistance arm is 50 centimeters. Okay, first thing we have to do is we have to change our centimeters into meters so that we are at the same units. And so 50 centimeters is equal to 0.5 meters. Okay, and then our mechanical advantage formula is the effort arm length divided by the resistance arm length. So our effort arm length divided by, there goes, effort arm length divided by resistance arm length. And so we're going to be doing 2 meters, our effort long, divided by our 0.5 meter resistance arm, and that's going to equal 4. And so our mechanical advantage would be 4 for that problem. Okay, for your lab today, you are building a catapult. And in your catapult, you have it in your book, but it says to use Blackline Master. So if we look at, let me share my screen. We have a Blackline Master here. I'm going to take a picture of it and email it to your parents as well. But if you have these pieces, if you have Tinker Toys, if you have K'NEX, you could probably use K'NEX as well. If you can figure out how to build it out of Legos, any of those things, give it a try. If you do not have any materials to be able to build that, that's okay. You don't have to scrounge around or look for or buy anything to build your catapult. But if you want to get creative, there's a number of different things that you can use to build a catapult. And so you can go online and look for ways to build a catapult out of things you have at home. Maybe you build it out of marshmallows and straws or toothpicks, I don't know, whatever you can. But see if you can build a catapult, and then your lab on 4.3.2b, you can go ahead and do the lab for that. So have some fun with this, do your best. And again, if you don't have pieces to be able to make a catapult, either get creative and see, you guys can work together on it. If you're together today, to build one. If you're at school, see if there's some materials at school you can use to build the catapult, and then go ahead and finish that lab. I can't wait to hear if you are able to build one and if you are successful with it, because that would be a lot of fun to hear about. All right, next time we're going to be going on to the next simple machine, which is a pulley. And so we will see you then.